I would like to get started so that our speaker can have the full time for his talk. We have the pleasure today of having Ricardo Daziano from the Civil and Environmental Engineering Department here at Cornell as our speaker. There is no lunch after this talk because he is a local speaker. But because he is a local speaker, he is happy to have you send him an email and follow up on whatever you hear today if you'd like to talk to him about it. So, the topic is very interesting. How many of you have plug-in electric cars of any sort?
Hybrid cars.
All right, so we have a couple of them here. And so it'll be interesting to see how these folks who have these cars resonate with your talk, and I hope you will ask questions.
Mm-hmm. Thank you. So good morning, everybody. I'm Ricardo Daziano. I'm a choice modeler. I'll be explaining a little bit about what choice modeling is first, then a couple of examples of that methodology, and then my own work, and then the specific topic of this talk. So this specific talk will be some work that we have been doing together with NYSEG and some other researchers here at Cornell, in particular with Brianna Morosa from Tatum Engineering and Charlene Hyde from NYSEG. So for starting, a little bit about what choice modeling is. My PhD is in economics, even though I'm based at the Civil and Environmental Engineering Department. So what I do is basically trying to understand how consumers make choices, right? Choice modeling. And we all have faced decisions when we're consuming something. And in particular, we face situations where we have alternatives. So for example, you're deciding where to go, where to stay for vacation. You go to Airbnb, and then you have different places. And then you start looking at, okay, what are the characteristics of the different places? We call that features or attributes of the alternatives. And then we're trying to model with these choice models what people are choosing. And for doing that, we can go to actual markets and see, okay, people chose this particular location at an Airbnb, or they bought this particular computer. In some other cases, we don't have actual market observations. And when that happens, we use something that we call choice experiments. So in this choice experiment, basically people are faced with a hypothetical buying context. And we present them with hypothetical scenarios that we call choice cards that present features of the alternatives, and then we force people to make a choice. And then we build models that are econometric models, or statistical models, to basically try to forecast what people would choose in a particular context. So I'll first give a couple of examples of work that I have not been doing myself, but it illustrates very well what choice modeling is able to do. So the first one is about credit cards. So what are the features to basically attract a bank customer to basically adopt a new credit card? So you are always facing this situation where maybe you're getting offers in your mail, and then they try to make that credit card attractive. And then people have used choice models to basically know what features of the card are actually attractive for the client. Another example of something I would have loved to have done myself, but I didn't. So this is another example where they use choice modeling to basically design the packaging, optimal packaging of chocolates. So in this study, people basically saw different packaging options that featured or highlighted different attributes. And then based on the choice models, they came up with, this is the actual final product, and how, for example, people didn't care about whether the chocolate was Swiss or not. It is actually from Switzerland, and you don't see it in the actual package unless you really read the small print behind, but because it was a statistically significant attribute in the results of the experiment. So one thing that we do with choice experiments and choice models that is very relevant in the context of environmental resources and energy is what we call inference on willingness to pay or willingness to accept. So we face a situation that is very common in the examples I was mentioning in environmental and energy applications. It's when there is no an actual market. So when there's a market, I can go to the supermarket and say, okay, how much does it cost to buy a yogurt? But if we are dealing with energy, for example, or emissions, what's the price of emissions we're emitting? It's not clear. So in that case, in economics, we have this concept of a shadow price. So there is a price, there is some valuation that we put to that environmental good, but we don't know what the amount of that valuation is. With choice models, we can actually give that value, that economic value, to the thing that is not traded in the market. So in particular, sometimes we basically discover that for a specific good or service or feature of an environmental good, people are actually willing to pay for that good. So they value that and they extract what we call utility from consumption. In some other cases, people see that as a loss, and then people are not willing to pay, they're willing to accept. And we'll see an example of that in this particular talk. So, motivating this from the point of view of energy, people are making energy-saving decisions all the time now. And I am particularly interested in what kind of energy-saving decisions people are making today, and then how are those decisions being shaped by technology. So in particular, something that I'm very interested about researching is choice of energy efficient durable goods. So in economics, we call a durable good a good that you buy and it lasts for many years. So there are several examples of that in the energy market. So a car is the clear example of that. You buy a car, you own it for several years. The average is 11 years in the US that you hold a car. Let's say you install PVs in your house, or you install a heater in your house. That's a decision of an energy-intense good that lasts for a long time. And then you have alternatives. You could choose, at the extreme, a very cheap, energy-efficient, a very cheap, non-efficient good, or a very expensive, energy-efficient good. So one is more expensive to buy, but it offers savings in the future. So this trade-off, and with choice models, we can understand that type of trade-off, how it's valued, how people value the savings in the future versus the investment cost in the present. So in particular, regarding this choice of durable goods in the energy market, I mentioned cars is a very specific example of that. And if we're talking about cars, as David was mentioning, right, one alternative is to go electric. And electric cars, they're growing a lot. In the market for electric cars, it is growing intensively. So here we have how that trend is growing worldwide. In particular, in the US market, in 2008, Tesla Roadster, it enters the market. Reintroduction of electric cars, the first cars, when they first were created, they actually were electric, and then the internal combustion engine was created afterwards. 2011 was when the Nissan Leaf started to be installed, and that was the first mass market product in terms of electrification of cars. Then by December 2019, 1.5 million cars in the US. In the specific month of December of 2019, the market share, so how many electric cars, plug-in hybrids and fully electric, that represented 5.1% of new cars being sold in the US. This graph shows some cars by model, basically. So the one that has led the market in the US is the Tesla Model 3, a very interesting case from a marketing perspective as well, followed by the Chevy Volt. So there's momentum in the market. I show you how it is increasing. There's currently 1.5 million cars in the US. And yet market shares are low, and adoption actually has been much slower than anticipated by by economists even. So, for example, to give you some more specific examples of why I'm mentioning that the market share is low. So, market share of new cars being electric, plug-in hybrids or fully electric in Tompkins County is 1.15%. In Manhattan is 1.24%. In New York State as a whole is 0.48%. And then that's the market share of new cars being sold. If you look at the stock of cars in the US, I mentioned, okay, 1.5 million cars. That sounds like a lot, but there are 278 million cars in the US. So that represents around 0.5% of the stock. So it's very, very little. So I've been doing some work that uses choice models that now we understand a little bit better what I mean by that. To, for example, compare that trade-off I was mentioning, and this is one of my papers, and you could look at my website and look at other papers. This particular one is looking at how people value the savings that they get from energy-efficient cars compared to the higher investment cost. This is another example of ongoing work, and this is currently happening in Canada, and I'm interested in how you present environmental information to the potential car buyer and how they react to that kind of information. So you may be familiar with the Monroney stickers here in the US, and in Canada they use basically the same, but it's in French and English because they're bilingual there. But it's mostly the same type of label. And then we are trying to see if we should redesign the labels in Canada. So within the context of electric cars, there are several challenges to make this a successful product in the market. But not only that, there are other challenges associated with electric cars. And in particular, one is, okay, if we assume that hopefully it's going to happen that electric cars are really becoming a successful product, then we'll face the challenge of large-scale charging. If we have a lot of cars that need to be charged, then we have to have power to basically power these electric cars. And then we'll face the problem of when the electricity is delivered to the cars and when people are demanding electricity to charge their cars. So related to this problem of large-scale charging and kind of anticipating solutions to that type of problem, there is currently a pilot which is called the Optimize EV pilot. And for this pilot, that I will be explaining what it is, and then the actual work that I'm presenting is related to this pilot. Basically, we're trying to see how to improve that interaction between the electric vehicles that people have and the electric grid. So there will be an eventual need for smart EV charging because of this problem that I'm mentioning of large-scale EV charging. So there will be no new load profiles. So basically, right, most people, 98% of people who own an electric car, they charge their car at home currently. And most people do exactly the same pattern. So they arrive at home, they plug their car in, and they leave it plugged in until the next morning. If there's no incentives, you just start charging the minute you plug your car in. Most people have a level 1 or level 2 charger at home. So it takes a long time for your car to be charged, and then you don't unplug it until the next morning. So you can think if you have a lot of cars doing this exactly the same thing of arriving, plug the car in, there's a peak load at 6 p.m. when people arrive home. And then basically anticipating this idea that maybe it's not a problem now when 0.5% of cars is electric, but if that starts to increase, then it will become a problem. So given that, we can think of the idea of deadline scheduling where, okay, it would be optimal to basically maybe create a delay on when the car is being charged. So the Optimize EV pilot program It's a pilot here in Tompkins County, and it's trying to do exactly that. It's a way of testing how basically allow customers to exchange control over when the electricity is being delivered to the car in exchange for a rebate. So the whole idea is to learn with this pilot how we can make the electric grid work best for the customer and for the grid itself. So there is an algorithm developed not by me, but by other researchers here at Cornell, so Ilian Bitar and Pauline Alexenkos, who is here. If you have a question about the algorithm itself, she's the one that can answer. So thank you for being here. So basically, the idea of this algorithm, it determines exactly when to charge the EV within a time frame and a target charge specified by the customer. So let's say you own an EV, you plug it in, but then you go to an app on your phone and you say, I would like to have, let's say, 80% of my battery tomorrow morning at 6 a.m. And yes, I'm allowing the utility to delay my charging. I just care to have that 80% at 6 a.m. in the morning. Okay? So that's the idea. And then people would have the choice of deciding, okay, no, I actually want to charge as I always did before, so just start now when I'm plugging it in. Or, yes, I'm allowing you, the utility, to charge later, but just make sure that I have that 80% at 6 a.m. But I don't care when during the night that happens. And then, so when that's being ensured, the actual charging happens sometime at night that basically ensures a discount for that person when they are allowing the utility to delay. So then basically the larger the flexibility that the customer is allowing the utility for when charging happens, the larger the discount that people will see. And the idea is that then you'll have this cluster of owners of EVs, and there'll be, now it's a pilot with just a few households participating in the pilot, but then when this is implemented in large scale, then you'll have a cluster of EV owners deciding this participation every night, and then the idea is that instead of having that peak load when people are charging without participating in this type of program, when they do participate and they allow the utility to delay the charging, then basically you flatten the load, and then you create or avoid creating that stress that would happen with that peak in the load. So you can think, okay, maybe there be other solutions. For example, you could think of time of use pricing. Maybe that will avoid the peak load, but time of use pricing, basically what it does is just shifts the peak load, right? So if people know that prices will be cheaper later, they'll just start charging later, not at 6 p.m. when they arrive home. They'll start charging at 2 a.m. when the electricity is cheap. But then everybody does that, and then you're just shifting the peak. But the idea of this type of deadline scheduling is that you basically manage by the flexibility that the owner is yielding to the utility to flatten the load. So before the actual pilot, we ran this survey, and the results I'll be presenting there based on this survey. So it was an online survey to basically understand this notion, which is a new notion of allowing the utility to delay charging. We wanted to see how people reacted to that, and then we also wanted to test actual characteristics of the program and the user interface of the app that was going to be implemented in the pilot as well. So the survey had different sections. One was a screening, then some baseline information about the user. Then we had the choice experiment that I'll be presenting in detail, user interface questions, as I mentioned before, and then general interest attitudes and media habits that will allow us to cluster and create segments of the user that we were interviewing. So data was collected in September to October of last year. We sent an invitation to basically people who registered their EVs in NYSERDA. And then we had a total of 462 people who responded. And these people are owners or lessees of EVs in New York State, upstate New York. So here we have a map, a heat map of where our respondents live in upstate New York. And in particular in Thompson County, we have 105 people that live in Thompson County where the pilot was going to be implemented. Here we have some sociodemographics of our respondents. We have some differences within Tompkins County, outside of Tompkins County, and it's relevant to make this distinction because we'll see that actually consumers within Tompkins County, they actually have a different reaction and attitude toward the environment and energy savings than outside of it. They are more concerned about the environment, actually, residents of Tompkins County. So another thing that we did with this data was to use customer segments of energy behavior, and that's based on a trademarked way of segmenting consumers that the Smart Energy Consumer Collaborative has created, and they allowed us to use this segmentation algorithm that they have. So this Smart Energy Consumer Collaborative has this algorithm, and that basically based on how people behave in terms of their consuming patterns of energy and their answers to some attitudinal questions, we can group them in 4 main groups. The first one of these groups is the green innovators. So green innovators, basically, they are leaders in terms of adopting energy efficiency products. They're very well educated. They feel comfortable with technology. They have high income. And they basically are green, as the name suggests. So there's not a whole lot of effort to make them adopt new technology that will save energy use. Then we have the tech-savvy protégés. They're younger. Their income level is still high, but not as high as the green innovators. So they're very interested, but they need additional motivation. They face some barriers. Some of these barriers may be the relatively lower income that they have compared to the green innovators. Then we have the movable middle. They are not very interested in energy savings. They're more cautious about everything in general, so they need to be convinced. So if you convince them, you can move them, and that's why the idea of this label that we have for them of being the movable middle. And then the last category, that's the most complicated one, is the energy indifferent. So the energy indifferent, they don't care. You try to convince them, and they say, you know what, we just don't care about energy savings. Some of them are climate change deniers, right? So very hard to make them change their behavior. These are the market sizes of each of the 4 segments nationally. So green innovators represent at the national level 20% of the population, tech-savvy protégés 25%, movable middle 29%, and then that most complicated group, the energy indifferent, 26%. Here there's some more quantitative characteristics of these 4 groups. So as I was anticipating, green innovators, higher income, more educated, and then that starts to get both are lower, especially in the energy indifferent group. So we took these segments and then we built the segments for the case of the respondents of our survey in upstate New York. In this case, we had green innovators, 32%, so higher. And I have another slide where I compare with the national percentages. Tompkins County, 39% are green innovators, so higher than before. So this is the one I was mentioning. So let's take a look at the green innovators, right? 39% in our respondents in Tompkins County are green innovators. 30% in the case of outside of Tompkins County. In total in the survey, 32% were green innovators, and that's compared to just 20% at the national level. So all of our respondents within and outside of Tompkins County, they were more green. One of the things, though, is that we were interviewing not just the general population, we were interested in the population of EV owners or lessees. So that's a particular niche of the market. So it's no surprise that we were capturing more people who are environmentally concerned. This is interesting in terms of market shares and what people own. So these are the EV, considering hybrids and full electric cars. 32% it's fully electric cars that people own in our survey, and then 67% is plug-in hybrids. And the most popular car, the Prius Prime, which is a plug-in hybrid. In terms of leasing a car, 35% full electric, 65% plug-in hybrids, and the most popular one, the Chevy Volt. But let's talk now about the actual experiment that we did regarding this optimized EV pilot. So we presented this thing of the idea of, suppose that your electric utilities introduce in a program where you have your EV, which we know that you do, and then we install a level 2 charger for free at your house, but in exchange for that free installation of the level 2 charger, you may have the option to allow the utility to delay charging. And if you do so, then we will offer you a discount. So we showed choice cards like this. This is just a sample, and then the actual values that people saw, they are varied according to their choices, and it's basically updated based on preferences. So this is just an example. We have 3 possibilities of the program here. It's described in terms of annual fee. Remember that we're offering this free installation of the level 2 charger, so you are getting something in exchange for joining the program. So we have the annual fee. Then we have the discount per charging session at home. As an average, how much they would get if they decide to delay, and that's represented by the attribute that is called hours of control yielded to the utility. So in this case, for example, the first program, people are allowing the utility to decide when to charge for a window of 4 hours, and then I could get a 5% discount in the delivery charge of the electricity for charging my car. Then we have bundle B. You're allowing it to charge for longer. The time window is now 8 hours, but the discount that you're getting is higher, 10%. And then you have bundle C, and they always had the option of, I don't like any of these 3 programs, and I want to opt out. And then again, we varied this, and then people saw 6 of these hypothetical programs. Then with this information, yes?
Did you give them the option of just buying the charger outright?
So when decided to opt out, then there was a follow-up question about that kind of yes.
How much is the charger?
Now I forgot the price of it. That's a very good question. Yeah.
With installation, it's like another 500.
Yeah. Thank you. I just forgot it. So with that information, then we run some models. So we had all the choices that people were making, looking at these choice cards. And then things that we can get is this willingness to pay measure. So let's first try to understand what kind of outcome we get from the model. So we get something that we call a marginal willingness to pay. So we have the features of the program. One was the annual fee. So this willingness to pay basically is in terms of incremental annual fee that people are willing to pay based on the improvements of the features of a program. So basically, if they decide to opt in, and then let's say that the discount, so this is a marginal valuation, if the discount is a 1% higher that I'm offering in a program, then people are willing to pay on average $3.20 more as an annual fee for that additional 1% of the discount. So everything is marginal. Then I'll discuss emissions, which were measured in pounds. So again, it's a marginal thing. So if I increase 1 more pound in the emissions that I can save by delaying my charging, I have a willingness to pay in the annual fee of the program. But you can see that I have 2 values there because basically we were able to obtain 2 valuations based on whether people reside in Tompkins County or not. As we were anticipating, people in Tompkins County, they are greener, and that's reflecting that they are willing to pay slightly more, $1.62 per pound, marginal pound being saved if they decide to delay their charging, versus 1.17 outside of Tompkins County. Then those 3 are willingness to pay, positive, so people are basically valuing the benefit of those features of the program. But you can see control yielded to the utility has a negative willingness to pay, so that's what we call basically a willingness to accept, right? So people don't like to yield control. So basically I tell them, okay, if you allow 1 more hour for the utility to decide when to charge the car, people are perceiving this negatively. They don't like that notion, even though they see the benefit from the savings in terms of emissions and the incentive in terms of dollars, the discount. They want a rebate of allowing the utility to delay charging. That rebate that they want per hour is $2.40 on average. So they expect basically compensation for joining the program in terms of that time frame that they are yielding control of when charging takes place. Some things that we learned from this experience that are very interesting for the actual implementation of the user interface and the pilot. So you can basically inform the discount that you're getting as dollars that you get, and also as a percentage. And in some ways, and this is related to something that you may heard of the concept of behavioral economics, so people reacted higher to seeing the discount as a percentage rather than dollars. So basically you see a higher likelihood of joining if you present the discount as a percentage than the actual dollar amount. Another thing that we were testing is, okay, there is some evidence in the literature that people get confused when they see pounds of CO2, and maybe they don't know how to process that kind of information, that they need some kind of equivalence. And then you can have seen, maybe these calculators that they show, okay, equivalence of trees being cut or cars being taken out of the street, equivalent to the emissions that you're saving and that you are saving. We have evidence in this case that people actually understood the pounds. They were reactive to that, and we can inform them directly about that information. But as we see, these are EV owners. They're highly educated. So in some ways, there's no surprise that we're able to actually understand perfectly well emission savings in terms of actual pounds. The last one is interesting for NYSEG, and that's why also we had the brand there, which is kind of an unusual feature of the program, but it's a marketing that NYSEG was really interested. We can also measure likelihood of opting in to the program. And again, this is measured marginally. And these are not probabilities of joining. Is given a baseline probability of joining the program, how much or much higher or how much lower your probability becomes given a marginal change in each of these characteristics. So, for example, if we increase the discount in an additional 1% more, then people are 5% more likely to join in a program like this. If we add 1 more hour in the time frame to allow the utility to decide when to charge the car, then people are 4% less likely to join in. And emissions, they are associated with a higher probability of joining. In some ways, more striking than these results is the following, is the generational divide. So millennials compared to older generations, you can see we have millennials, Gen X, baby boomers, and then we have older generations than baby boomers. So these percentages are relative to older generations, and then millennials are 284% more likely to join than older generations. So they see more the value of the program, they understand better energy savings and this notion of, optimizing the interaction with the energy grid. So this is very similar to that graph that I had with the willingness to pay for the discount, the emissions for Tompkins County, outside of Tompkins County, and it's exactly the same, and then that willingness to accept or the compensation that they want for giving up control of when charging takes place. The difference of this graph with the previous one is that this one is by segment. So we mentioned those 4 segments of consumers. So we had the green innovators, the tech-savvy proteges, the movable middle, and the energy indifferent. So we have a lot of information here. I concentrate on 2 here, control, and then the pounds being saved for Tompkins County. So you can see that basically the lightest color is the energy indifferent. They really are disliking this idea of yielding up control of the charging of their car. So they want a higher compensation. The green innovators, they still want a compensation, but the compensation they're asking is $1 versus almost $4, $3.72. So much higher for the energy indifferent. And then the trend is reversed for the valuation of the emission savings. So for each pound of CO2 being saved, the green innovators, they're willing to pay $3.80 more in the annual fee of the program. And the energy different, they see the value, but they're willing to pay much less, $1.38. So this is kind of summarizing again the same kind of notion and comparing the values that you get with the segments, and in general makes sense with what you would expect from the definition of the segments. But then one thing that you could do is we can categorize households in a particular segment, and we can expect how they react to a program like this of a smart EV charging. This is another way of visualizing how people are reacting to the characteristics of the program in terms of the discount that we can offer, the hours of control, that they're yielding and the pounds that are being saved, again, in terms of marginal changes of it. And you can see how the energy in different segments, they care mostly about the hours of control, and the green innovators, that's just 11% of the total. So they care, but they much less compared to the other groups. So from this relative importance and from how they are exhibiting this willingness to pay that they're eliciting from their responses to the choice experiment, we can learn that the energy indifferent, they desire to keep full control of their charging, but are open to potential discounts. So this is the interesting thing. So the energy indifferent, they're not really motivated to maybe allow the utility to delay charging because of the environmental benefits of doing so. But if you offer them an economic incentive, then they are in. So they're energy indifferent, but they're not money indifferent. So if you offer them enough dollars, they'll be allowing or accepting energy efficient actions. Whereas the tech-savvy proteges and the green innovators, they actually value much more the emission savings, but they still are economic agents, so they still value the economic incentive, and they'll be reacting to a higher discount that you could offer. So this is a very interesting exercise that we can do. So once we have the responses, we can take what we call a representative consumer that has the average valuations that we get from the choice models. And then we can build different programs. And then based on that, we can see what's the total value that people are assigning to that specific program. So let's concentrate here first on the first row here. So that would be a program that, let's say, offers a 2% discount per charging session where the user is allowing the utility to delay. The time frame that you're allowing the utility is 8 hours. And because of the electricity being shifted to greener renewable resources for generating the electricity, then you're saving 10 pounds of CO2 because of delaying your charging. So that's the program. Then based on that, marginal willingness to pay now is total and non-marginal anymore. And for each segment, we can determine how much they value that specific program. So we can see that the three segments that are greener, so the movable middle, the tech-savvy proteges, and the green innovators, they all value that program positively, so they would join because they're having a positive willingness to pay in total for that program. So not only they would join, they would also actually pay an annual fee for joining that program. The energy indifferent, given those three characteristics that I mentioned, 2%, 8 hours, and 10 pounds of CO2, they have a negative total willingness to pay, and that means that they would not join the program. So then, these are counterfactual scenarios. So let's say we keep the discount the same, we keep the time frame the same. This is the second row, but somehow we manage to have greater environmental benefits. So we're increasing the emission savings from 10 pounds to 35 pounds of CO2. And in that case, all segments, even the energy indifferent, they would see the value of the program and they would join because of the positive willingness to pay. This is outside of Tompkins County, and you can see that because outside of Tompkins County people are less green, there are more red valuations appearing in this table. The hypothetical programs are exactly the same, but outside of Tompkins County, then people would be basically less likely to join a program of smart EV charging. So a couple more things. We also ask I don't have here your specific question, but we did ask if they would install a level 2 charger. But in this particular one, we were interested in, okay, if you decide not to join this charging program, would you prefer time of use rate plan? And 19% said yes with a rate that differs hour by hour. Then in green, most people said yes with a fixed rate for most daylight hours, so basically kind of block periods. And then 15% that no, they wanted just a fixed rate throughout the day. So in conclusion, successful design and deployment of energy-saving programs and services crucially depends on an accurate characterization of customer preferences. And the type of work that I do is basically looking at those consumer preferences and how we can use those to inform things that you do, which is more on the technical side. You're designing the technology, you're engineers with an energy-saving goal, but then it is the consumer who will be using the technology, and then we need to understand not only how people are basically interacting with the user interface of that technology, we're also interested in, are people willing to join such a program or the technology that we're offering? And if they are not, maybe how we could convince them to do so. In this particular case, we can play more and basically determine, for example, what would be the optimal incentive, economic incentive, for people to actually make the utility, make the decision on when to charge the car. So this particular choice experiment has provided evidence that both the monetary discount and the emission savings actually are attractive. Even for the energy indifferent, we were seeing that those amounts could potentially be attractive for a customer to join this idea of a program where people would allow the utility to decide when to charge the electric car. So one thing that the pilot is testing is the idea of the time frame window to charge the car. Another thing that we would need to test later is this notion that the trade-off is not only when you want the car to be charged the next morning and whether you're allowing the utility to decide when charging takes place or not. There's also the question of maybe deciding on a particular day, I don't need 100% of my battery the next morning, maybe need 80%, and maybe it would make sense for the optimal energy delivery that maybe people charge, let's say, 50% or 40%, so maybe we would need incentives for people to decide a state of charge that is much lower than they would actually desire, but then if there is the correct incentive, maybe they would do so. So that's another thing that we could do in the future. And that's my presentation. Thank you.
Questions? Did you get your question answered?
So one thing that's not completely clear to me is the setup of these bundles and how this came about, because from looking at them briefly, I thought them to be quite complicated to understand, to be honest, and how you mentioned briefly that maybe NICEG had particular preferences in this regard. If you could explain that a bit.
Yeah, so designing the bundles, it's a question of trade-offs too. You have to basically look at the requirements that you need for the study and the technical goals and informing the pilot. There's a lot of evidence in the literature that people are able to process very complex choice tasks. This actually is not complex compared to what people are cognitively able to respond to. We did pre-testing in focus groups too to check that people were understanding what we were presenting. There was, in part of the survey, we actually explained more than I did here about what each element in the bundle meant. And then there are trade-offs that, as a researcher, to be honest, I wasn't really interested in presenting this, okay, is it Google, is it Amazon, or is it NICEG? But then that's a question that NYSEG was really interested and they were trying to push, and yeah.
Yes.
In terms of like the algorithm itself, does it allow you to choose like, oh, I have a preference of charging my car like right before I'll get in it so the battery will be warm? Like in the winter, you can just record it. Is it?
Sorry, so the question is, can
Can
you
you put a
schedule?
preference of like when in the night?
No. So the idea behind the algorithm is basically you're yielding control to the utility to decide when the charging occurs.
Could you not like
So you can,
then
in
a massive
principle,
group of people that like, oh, I prefer to charge here and like these three.
so one way you can sort of implement this yourself is by if you connect the vehicle in the middle of the night, you're implicitly enforcing this constraint. But I mean, at that point, it's a question of how much flexibility you're really giving the utility, right? So if you want the vehicle to be charged to a certain amount right before your deadline, then you're not really allowing the utility to schedule charging, right?
Okay, I think we better let people evaporate, and so why don't you come up and ask your last questions? Thanks very much again.